in lesson 3.2, we were given real zeros that we could work with. How many each represented? So let's say we had x is equal to 4 and it was able to be counted twice. Then we could utilize synthetic division to help divide that out for us. But what if we don't have any given real zeros? So the ancient mathematicians, if they're trying to graph these and they weren't given a real zero, how do we find what they are? Because you and I don't have time to just randomly put numbers in and synthetically divide until we find one that has a remainder of 0. We would be here all day. You don't have that kind of time, and I certainly don't have that kind of time. So we've got Cauchy's bound here. This rule tells us where we could limit the interval of where the real zeros may lie between. And what we're going to be doing here is utilizing the coefficients of the polynomial when written in descending order to help identify what values we may look at. So notice in our top row here, we need the absolute value, and we're going to start with looking at the absolute value of the constant over the leading coefficient. Then we'll go to the next coefficient and put it over the absolute value of the leading coefficient. And we'll continue this until we run out of coefficients, always over the leading coefficient absolute value to determine what is the largest value here. And so in this first example, we've got 2x to the 4th plus 4x cubed minus x squared minus 6x minus 3. So I'm going to start by looking at the absolute value of -3 over the coefficient of my leading term, the absolute value of that. This gives me 3/2. Then I'll go to my next leading, or my next coefficient, the absolute value of 6 over the absolute value of my leading coefficient. This is 6/2 or reduces to 3. Then we go to 4, our next coefficient. I have the absolute value of 4 over the absolute value of 2, which is 4/2, which is 2. Now I'm going to look for the largest of those numbers. That's what we get to use. I'm looking for the largest number. 3 happens to be that largest number, and this gets to be our m value that we're going to put into this interval formula. So I grab the largest one. My zeros are going to be in the interval then between the opposite of our m value 3 plus 1, comma, and our m value plus 1 included. So our zeros are going to be in the interval between -4 and +4. That way I don't have to check like -5, -6.25, or anything weird and wonky. I know that all of my zeros, my real zeros, are going to land in between these two numbers here. And that brings us to the rational zero theorem. Well, what could those numbers be? Because as you learned with our last section, that they always don't have to be whole numbers. They could be decimals, and they could be ugly decimals sometimes as well. So we need to be able to identify what numbers we should potentially be looking at. So we've got our polynomial, and it has a degree of larger than 1, and we have our list of coefficients that are there that are integers. So if r is a rational zero of f, then r is of the form plus or minus p over q, where p is a factor of the constant and q is a factor of the leading coefficient. So we are only interested in looking at the constant and the leading coefficient. So I'm going to look at my leading coefficient, which is 2, and I'm going to look at my constant, -3. So P is a factor of the constant term. So we're going to say -3 is P. And what are the factors of 3? Well, our factors of 3 are 3 and 1. They're the only values that divide into 3. Now I'm going to look at 2. 2 is Q. Q is a factor of the leading coefficient. What are the factors of 2? well, 2 and 1. Then we're going to take every single combination and make p's over q's plus or minuses. So I'm going to have plus or minus p over q. And it doesn't matter how you write these. My p values are 3 and 1, and my q values are 2 and 1. So all the combinations of p over q that we have. So if I start with 3 as my p, I'll have plus or minus 3 over 2. I'll also have plus or minus 3 over 1. So I did all of my factors of 3 over all of my factors of 2 and 1. Now I need to do the factor of 1 with p, plus or minus 1 over each factor of q. 2, and plus or minus p, we have to do 1 over the 1 on the left. And then, of course, we will want to simplify. I'll get plus or minus 3 halves, plus or minus 3, since 3 over 1 is 3, plus or minus half, and plus or minus 1. Notice all of these are in the interval between -4 and 4. So these are the values that we will want to try in order to reduce our polynomial and utilize our thoughts from the previous section. So now that we know that these are the possible solutions, we've got 8 options, right? 4 positives and then 4 of the negatives. We can start looking at each one of these and using our synthetic division to see if we can find a reduced polynomial if there is a remainder of 0. So on slide 3, I've got the graph of it because that can certainly help us identify if we maybe have a multiplicity depending upon if it goes straight through or maybe it just dips down and touches. So we also know the interval for which we should really focus our efforts on, which should be between -4 and 4. Even looking at our graph, here's 4. Notice all of our zeros do in fact, here's -2, so -4 would be somewhere over here. Notice all of our zeros do in fact land in between -4 that we found with Cauchy's bound. I do know, so using graphing technology and using Cauchy's bound as a guide, which we just did. Then use the graph to shorten the list of possible rational zeros from the theorem. So we had found that negative and +1, negative and +3, etc. were all possible solutions. So then we'll use synthetic division to find all the real zeros and their multiplicities if needed. So use graphing technology to narrow down the list of possible rational zeros and then begin. Well, I see that a nice possible rational zero is in fact -1. So I know that -1 is a real solution by putting all 3 of those pieces together. The bound, the rational zero theorem from the previous slide, and the graph. So -1 is a real solution. So then let's use -1 with synthetic division to find a reduced polynomial. So I grab 2, 4, -1, -6, and -3. I bring down 2 and then begin multiplying. -1 times 2 is -2. 4 minus 2 I know is +2. -1 times 2 is -2, so when I add we have -3. -1 times -3 is +3, so when I add I have -3 yet. -1 times -3 is +3, so I have 0 left over. Perfect, we know it was a 0 anyways. But maybe it's a double solution. So maybe it has a multiplicity. I should say greater than 1 here. How do we know? We'll try again. Maybe I get to count -1 twice. We know we need 4 solutions. I see my other 2 solutions are kind of not very nice numbers. So maybe I get to count -1 twice. If so, let's use this and find a reduced polynomial. So I'll start over where we left off with our reduced polynomial and see what happens. Always bring down the first term. -1 times 2 is -2, so we have 0. -1 times 0 is 0, so I have -3. Ooh, this is looking good for us. -1 times 3 is +3 with 0 left over. So it is a double solution. So -1 gets to be a multiplicity of 2. But what are the other solutions? Well, I know that this is now my reduced polynomial where -3 is the constant, 0 is the coefficient of x, and 2 is the coefficient of x squared. Now I have 2x squared minus 3, set it equal to 0. At this point, we can add 3 to both sides. So I have 2x squared equals to 3. Divide by 3, so x squared is equal to 3/2. And then take the square root of both sides. So x is equal to plus or minus the square root of 3/2. But we want to rationalize the denominator. This is the same we know as square roots 3 over square roots 2. To rationalize the denominator, we'll multiply the numerator and denominator by square roots of 2, giving us plus or minus square root 6 over square roots 4, which reduces to square root 6 over 2. So now we've rationalized that denominator by getting rid of the radical in the denominator. Our 4 solutions then, because there's 2 of them here, and we get to count -1 twice because it went through twice. So x is equal to -1, -1, square root 6 over 2, and negative square root 6 over 2. We found all 4 solutions. We have x equal to -1 since it says to state the multiplicities. Multiplicity 2, excuse me. And then each one, square root 6 over 2 and negative square root 6 over 2. These have multiplicity is each of 1. Let's try another example. Here we've got x to the 4th plus x squared minus 12. When I'm looking at the graph to help us, those aren't very nice numbers. So we're going to definitely need to use Cauchy's bound to determine where all of our real zeros should lie and what we can do to find the other real zeros. So we know we need 4 solutions, and I'm only seeing 2 here. So this is kind of foreshadowing into our next lesson about what we do if we only have the 2 real solutions about the other 2, and we'll talk about that in a moment. First of all, let's look at, let's use Cauchy's bound to determine our m and our m value. So I look at 12, and I'll take the absolute value of 12 over the leading coefficient of 1, which is 12 over 1 or 12. And then I'll have the absolute value of 1 over the absolute value of 1, which of course is 1. So our m value is 12. Thus, Cauchy's bound is going to be the opposite of our m value plus 1, comma, our m value plus 1. So all of our zeros should lie between -13 and +13. A little large of a value here, but it's certainly, when I'm looking at the graph, our values are in fact in between. Then let's use the rational zero theorem to determine what possible rational numbers these could be. So I'm going to look at P and Q here. 12 is my P value, and Q is my 1 value. So when I'm looking at factors of P, so the factors of 12 are 1, 2, 3, 4, 6, and 12. The factors, this one is easy, of Q, just 1. So easy enough to find all versions of P divided by Q. So I'll take 1 plus or minus 1 over 1 plus or minus 1 over the, 2 over 1. Don't get them backwards like I just did. Plus or minus 3 over 1 plus or minus 4 over 1, 6 over 1. Apparently I was looking ahead. And plus or minus 12 over 1. Of course, these all simplify down to plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, etc. But if I look at my graph to help me, so I graphed using my graphing calculator, none of these work. None of these work at all. That wasn't very helpful. So I'm going to have to utilize some other strategy. Perhaps I can factor, because if I look at x to the 4th plus x squared minus 12, we have a trinomial. Perhaps we can factor. So what might multiply to negative 12, but yet add to positive 1? So remember 12 and 1, so ignoring the x to the 4th and x squared, this is a trinomial. I have 4 times negative 3 will work. I know this then factors into x squared plus 4 and x squared minus 3. I know this because I could certainly distribute. X squared times x squared, of course, is x to the 4th minus 3x squareds plus 4x squareds minus 12. And when I combine like terms, I end up back where I started. So that's a double check for us to make sure we're on the right track. All right, now that we've got it factored, we can set each factored piece equal to 0. So I have x squared plus 4 equals to 0, x squared minus 3 equals 0, and then solve each one independently. So I'll have x squared equals negative 4, and when I take the square root, oh, we have a problem. These are non-real solutions. So of the 4 that we need to have, of the 4 solutions we need to have, 2 of them are non-real, and we're going to deal with that Thursday, during Thursday's lesson. However, our real solutions that we are able to see, we can add 3 to both sides, and then I can take the square root of 3. So x is equal to plus or minus the square root of 3, which are, this would be negative square roots 3, and this would be positive square roots 3. The other 2 are ones that we cannot see because they're imaginary. Again, we will talk about that in our next lesson. And each one of these has a multiplicity of 1. All right. Doesn't hurt to have as many examples as possible to see the different kinds that we might be able to see. We've got 2x to the 4th plus x cubed minus 7x squared minus 3x plus 3. I've got the graph on the right-hand side. We need to find 4 solutions. Again, with the last example, some may be real, some may not be real. But when I look at my graph, they're probably all going to be real because I can see that there are 4 places it crosses the x-axis. So let's start off by looking at Cauchy's bound to determine on which interval the real zeros need to lie. So I'm going to look at each coefficient and put that over the absolute value of our leading coefficient. I'll have the absolute value of 3 over the absolute value of 2, which is 3/2. It will be repeated with this guy since I'll have the negative absolute value of 3 over 2, which is still 3/2. Then I'll have the absolute value of -7 over the absolute value of 2, which is 7/2. And then the absolute value of 1 over the absolute value of 2, which is 1/2. So it looks like our largest value is 7/2 because that's 3.5, so this is M. And then our bound will be the opposite of 3.5 plus 1 and 3.5 plus 1. Oops. Bracket. Which of course gives me between -4.5 and +4.5. Which if I look at my graph here, 1, 2, 3, 4, here's +4.5 and -4.5. Our zeros are in fact all in between. Graph using our graphing calculator and use the rational zero theorem to determine a list of all possible rational zeros. So in this case, I need the leading term and the constant term. So +3 is our P, +2 is our Q. We need all factors of P, and all the factors of 3 are 1 and 3, which is not too bad, and then factors of Q. So 1 and 2, and all positive and negative versions of P over Q. So I'll start with my P value, plus or minus, we'll start with 1. So 1 over each Q value, 1 over 1, 1 over 2. So I did this one, now let's go on to 3, plus or minus 3 over 1, plus or minus 3 over 2. So all of them are accounted for. And notice every single one of these numbers is in fact within Cauchy's bound. We graphed, and now looking at our possible solutions, I see I have -1 as a nice real zero. And -1 just happens to be one of our possibilities as a theorem. So let's use then -1 to reduce the polynomial. So we'll start with -1. I have 2, 1, -7, 3, and 3. I didn't have any missing pieces along the way. I'll bring down 2. Let's see here. -1 times 2 is -2. When I subtract, I have -1. -1 times -1 is +1, so then I have -6. This will give me +6 when we multiply. Oops, this should be a negative. I apologize, it didn't stick. So then I have +3, -3 when I multiply, and a 0. Shouldn't surprise us. We do see that -1 is in fact a solution. Let's keep reducing. Because I also see half is a real solution as well, and half is just so also happens to be part of the rational zero theorem that we found. So let's keep reducing, this time using half. We'll pick up where we left off, so 2, -1, -6, and 3. You also certainly could have started off with half and then did -1. So the order doesn't matter. I was just working from left to right. So I bring down 2. Half of 2 is 1. When I add, I get 0. Half of 0 is still 0, so I have -6. Half of -6 is -3, so I end up with a 0. We do now have our reduced polynomial. So this is our constant. 0 is our x coefficient and 2 is our x squared coefficient. My reduced polynomial is 2x squared minus 6 equals 0. Now we can solve because that's going to help us find these other two in their exact form. So I'll add 6 to both sides. Divide by 2. So then x is equal to plus or minus the square root of 3. My solutions then are x is negative 1, half, positive square root 3, and negative square root 3. Each with a multiplicity of 1. All right. And our last example, doesn't again hurt to see possibilities here. I know I'm going to need 4 solutions. They could be a combination of real or imaginary. Notice here that we're dipping down and touching the graph. That tells me that we have an even multiplicity when we dip down and touch the graph. So it's very possible that each one of the solutions we see when we graph get to be counted twice, and we only need 4 solutions altogether. Let's use Cauchy's bound to determine the interval which we should have the real zeros at. So we'll start off by taking each coefficient, dividing by the absolute value of the leading coefficient. I'll have absolute value of 1 over the absolute value of 36, which is 1/36. The absolute value of 2 over the absolute value of 36, which is in fact 1/18. We'll have the absolute value of negative 11 over the absolute value of 36, which is 11/36. We'll have the absolute value of 12 over the negative 12 over the absolute value of 36, which of course is 1/3. It looks like our largest value is 1/3. So 1/3 gets to be our m value. So our bound says the opposite of our m value, 1/3 plus 1, and then 1/3 plus 1. This is then going to be negative 1 1/3 all the way to positive 1 1/3 included. So on my graph here, I don't think I've got it set. So yeah, here's 1. So here would be about 1 1/3. There's 1, so about here. And in fact, yes, our graph, our zeros are in between that bound. What are the possible rational solutions? So of course we need our P and our Q. We've got our P value is 1. Oh geez, look at our Q value. Q is a lot. So factors of P, just 1, right? Just 1 is divisible by itself. And we have factors of Q, and so factors of 36. Oh boy, okay. 1, 2, 3, 4 is divisible. 6, 9, 12, 18, and then itself. So of course our solutions then could be plus or minus all P over Q. Well, thank goodness there's only one P value, because then we'll have plus or minus 1/36 plus or minus 1/18. Sorry, I'm going backwards. Plus or minus 1/12 plus or minus 1/9, 1/6, etc., 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 right? There's a whole bunch of them. All of which, all these numbers happen to be, of course, in our range, which is good to see as possibilities. And so now I'm going to look at my graph using our calculator, find all the real zeros. We know that negative 0.333 is negative 1/3. And that half, of course, is half. So it doesn't matter where we start. I'm going to start with half just because it's positive and easier value to work with. So I'm going to start with half and try to find and reduce my polynomial. So using my coefficients, and I see that they're all in descending order. There's no missing pieces. Bring down 36. Okay, so half of 36 is 18. That's great. So we bring that over there. Negative 12 plus 18 is 6. Half of 6 is 3. So when I add these, I get negative 8. Half of negative 8 is negative 4, which gives me negative 2. Half of negative 2 is negative 1, which is a 0. Clearly we see that. But I'm cautious here because I do see that my graph dips down and touches. That tells me that I have an even multiplicity. So half probably gets to be counted twice here. So I'm going to use my reduced polynomial and see, does half go in a second time? So I'll have 36, 6, negative 8, and negative 2. Always bring down the 36. Half of 36 is 18. 6 and 18 is 24. Half of 24 is 12. When I add, I have 4. Half of 4 is 2, and there we go. Multiplicity 2. I can't have multiplicity 3 because that would mean it would go through the graph. And I know I can't have multiplicity 4 where it gets to be counted 4 times because I do see that there is another one there that we have to try. So now I'll work on negative 1/3. So from here, I'll do negative 1/3 and reduce my polynomial just to verify. So I'll have 36, 24, and 4. So I bring down 36. Negative 1/3 of 36 is negative 12. So when I add, I have 12. Negative 1/3 of 12 is in fact negative 4. So I have 0. This leaves me then with my constant and 36 being the coefficient of x. This is the same then as 36x plus 12. And if I solve this, set this equal to 0, I'd have 36x equals negative 12. X is negative 12/36. And then, of course, that gives us negative 1/3 with our multiplicity of 2. So we end up with x is equal to 1/2, multiplicity of 2, and we also have x is equal to negative 1/3, multiplicity also of 2. I highly recommend, my friends, to utilize just these 4 steps to help kind of verify, practice finding Cauchy's bound, practice finding the real zeros, seeing if those real zeros match into Cauchy's bound. Use our graphing technology so that you're not having to test everything in the rational zero theorem. So that's where we're using graphing technology to help us a little bit so that we're not stuck. I don't want to say wasting our time, but we could use our time more efficiently by using the graph to help us identify what those real zeros are. In our next lesson, we'll tackle what happens if we have non-real zeros and how do we deal with those? How do we find those? But this takes care of everything in this part.